So if this was a CH2OH, it would still be at the top because this carbon doesn't have any oxygens attached to it. Okay, and then you go back, we did the same thing, prioritized, so this is 1, this is 1, 2, this is going to be 4, so we're going in this direction, okay? So we're going clockwise, and again, clockwise, and the Fisher projection is the same as the reverse dash and wedge. Okay, so if you learn this, you know, this setup up here, you've got Fisher. There's only a couple different things with Fisher projections or Fisher structures that you can't do, or you have to do a little different. We'll look at those. All right. All right. So here's some of the guidelines for Fisher projections or Fisher type of drawings. Again, you want to have the highest oxidized carbon at the top. So I just went through that. Carboxylic acids, aldehydes, CH2OH. That would be your order of oxidation. Carboxylic acids would be at the top. Okay, we'll look at examples so you can see how that works. Now in this system, if you're trying to make a decision whether, and we'll look at these in a second, whether if you have 2 of these drawn, you're trying to decide are they superimposable on one another, you can only rotate them 180 degrees, whereas with a dash and wedge you can rotate, twist, turn, whatever you want to do. But with this system, you can only rotate it 180 degrees and you slide it over, see if it fits over top of one another. Okay, so these turn out, what we're looking at is this structure and this structure here. Okay, what they did is they rotated this 180 degrees, and that's how they got over to this. Okay, but you can only rotate them 180 degrees. You can't do 90. And okay, and there's a bunch of tricks with these. I'm going to show you as many as we can. Again, here's an example. This is sort of the dash and wedge. Carboxyls are sort of going back behind the plane and the methyl. The hydrogen and the oxygen are coming out. Essentially what they did in this case is just squash this down, sort of stepped on it, like push it down, flatten it out, and that's what the structure is going to look like over here. Okay. Again, we're going to look at examples of how you jump back and forth between dash and wedge and Fisher, but probably not till Monday. So here's an example. Here's like a question. Here's a couple of mirror images of one another that are again drawn in a Fisher type of projection. And the question is, they're mirror images of one another. Are they enantiomers? In other words, is this a chiral center? And the answer in this one turns out to be yes. But what you do is that's what I was trying to show you here, is you rotate this 180 degrees. So essentially you're taking this group, pulling it down here, and this pulls the hydroxyl group over here, and the hydrogen comes over here, okay? And then you slide this across in your mind's eye, if you will, to slide it across and see if it's going to overlap here, and it turns out in this case it doesn't. So the question is, are these enantiomers, non-superimposable mirror image? Yes. They're non-superimposable on one another. So that's definition of an enantiomer. And that happens to be a chiral compound, okay? If they're not, then it's not chiral, and they're the same compound. Okay, so here's what I have up here, you guys. This table, this whole table is drawn a little bit different, but you definitely want to be really familiar with that to be able to do these problems in this chapter. And I was just showing you. I was just doing one down here. Again, where you got an aldehyde at the top. You have a CH2OH group here. This is drawn correctly because the aldehyde's a higher oxidation state than the methylene hydroxyl group or the methylene alcohol. So that's drawn correctly. There's no problems with that. So again, we're going to prioritize hydrogen. We're going to look what's attached here. Hydrogen is 1, so it's going to get 4. Hydroxyl here, the alcohol group is oxygen, so it would be 8, so it's going to get number 1. So we got those taken care of. Then we just have to make a decision between these two carbons here. And again, this has a carbonyl attached to it. If you think about it, that carbonyl is almost like you have another oxygen on that carbon. The way the system that Wade talks about breaking these down. So this really has 2 oxygens attached to it, and this one has 1. So this gets a higher priority over the one at the bottom. So the numbering goes 1, 2, and again, it looks like we're jumping over number 3 in this case, but we're going to 1, 2, 3 in this direction. And again, we're going in a counterclockwise manner. And then if you look here, counterclockwise in the Fisher system is R. So it's just a reverse of what we started out here. Just a reverse. Okay, here's another example. Again, in this case, the reason I put this in, I'm just trying to drive home this idea about the oxidation state. Again, if you look here, you got a CH2OH at the top, has a higher oxidation than this methyl down here. It's just 3 hydrogens. So this is drawn correctly with the higher oxidation at the top. And then we're trying to make a decision on these two. They're mirror images of one another. Again, the oxygens are nose to nose. The methylene hydroxyl groups are lined up fine. The hydrogens are sort of back behind here. And the methyl groups are lined up sort of nose to nose here. So their mirror image part of it's perfectly fine with this. Rotate this 180, so I'm going to rotate this 180 degrees, and then look back over here to see if it sort of sliding across. Does it sit over the top? It doesn't fit on top of that. So it's non-superimposable on its mirror image. So these are enantiomers of one another. And again, if you prioritize, I did that here, where again, oxygen takes the highest priority, hydrogen's number 4, and then you have to make a decision between a carbon that has oxygen on it and one that has 3 hydrogens on it. So the one with the oxygen gets a higher priority than the methyl group. So this is the right priority. And again, we're going to go 1, 2, and it's almost like we're going to jump over number 4 down to number 3. But in this case, we're going in a counterclockwise manner. And again, counterclockwise in the Fisher is going to be the S. We're going to jump over here. We're going to do the same thing here. We're going to do, this would be 4, or excuse me, this would be 1. This is 4. This is 2. So we're going in the clockwise manner, and that's going to be the S. Okay. So these are enantiomers of one another, non-superimposable mirror images. Okay. So let me go through a few tricks. Sometimes this one happens to be, it just happens to be drawn as a mirror image. But sometimes you'll get these problems. And the reason I put this in here is because I've seen these problems on the organic part of the DAT and the MCAT and the ACS exam, and on the, I don't know if any of you ever go to graduate school in organic chemistry, they throw that in here on that as well. So that's why I put these in here. Wade doesn't talk much about these in the book. But in this case, if you look here, these are definitely mirror images. But sometimes they draw these where they're not mirror images, and they're going to ask you, are they chiral or are they the same molecule? Remember, you have to have a superimposable mirror image to be chiral. So anyway, if you look here again, mirror image is perfectly good with this, and if you rotate this 180 degrees, and that's kind of what I slid this across, and I looked to see if this would fit over the top, and it doesn't. So you could looking at this, you could say that non-superimposable mirror images. Certainly, these are 2 enantiomers, and this is a chiral. These are chiral compounds. Okay. All right, that's one way. The last one I want to well, not quite. Okay. So this is an example of going from, essentially, this is what these molecules are going to look like if you put them in a ball and stick, jumping from here essentially down to what would be a Fisher type of projection. Although the carbon is left in here, okay, a lot of times you're not going to see the carbon here. This crossroads is indicating you have a carbon, but a lot of times it's not going to be drawn in here. One thing I wanted, before I get away from this slide, okay, these are, if you look here, these are non-superimposable mirror images of one another. But I want you to look over here. Okay, these here, again, they're mirror images of one another, but they're superimposable on one another. Okay, and what we talked about on Wednesday, there's a plane of symmetry through here. Okay, there's a plane of symmetry through there. So if you find a plane of symmetry, even though there's chiral centers, doesn't rotate plane polarized light, they're superimposable on top of one another, you have a plane of symmetry. These are called mesocompounds. These are mesocompounds. All right? And mesocompounds won't rotate plane polarized light. And they're not chiral. So this is an example of it. We're going to look at some symmetrical molecules where we talk about that dichloro, the cis dichlorocyclopentane is a meso compound as well. So anytime you find a plane of symmetry, so the top and the bottom of here essentially are the same, you're talking about a meso compound. Now, we're not quite there yet, but we're going to get there real quick. These are enantiomers of one another. If you're talking about one of these compared to this one over here, doesn't matter, these are the same compound. But if you're comparing this one and this one, we're talking about diastereomers. Diastereomers have the same connectivity, but they're not mirror images of one another. Okay? In other words, you have a hydroxyl group attached to this first carbon, same thing over here. Here you have a carbon attached, or a carbon with a hydroxyl. I mean, the attachment's all the same, but they're not mirror images of one another. So, say you were comparing this compound to this one over here, you would say, you know, they're enantiomers of one another. And we're looking at a bunch of examples of that so you can see that. But anyway, we'll talk more about that Wednesday. Okay, here's another example of that. Plane of symmetry. Okay, plane of symmetry. Again, mirror image. These are mirror images of one another. Okay, but if you rotate this 180 degrees, it's going to fit right over here. But look for that plane of symmetry. These two are meso compounds of one another. Again, chiral centers. That's what you see here. There's chiral centers in them, but they don't rotate plane polarized light, and they're not chiral. Okay, these are referred to meso compounds. Okay, all right. I've had enough. You've had enough. Okay, so you guys, just one thing. Remember what I said on I don't know, let's see, I think Wednesday or something like that. This stuff is new, I think. So get in, burrow in it, get down in it. There's some great problems in the book. Get working on those. And the other thing is, I will caution you, if you work a problem in the book and you say, you know, I think that's right, and I look at solution manual and say, oh, I got the wrong answer. Come and see me. Because there's a couple of in the solution manuals, there's answers that are not right. So I'm just giving you a hint on that. You know, I mean, you people that wrote these books are, you know, established organic chemists, and they still make mistakes on this stuff. Okay? So if you do some of those problems and you're scratching your head, this looks like, I think I did this right, but I got the wrong answer. Come and see me. I think I found most of those, but I ain't going to tell you what they are. You can find them. Kyle.
How do you say the molecule rotate plane polar image?
How do you say doesn't rotate plane polarized light?
Plane polarized.
Plane polarized. Don't ask me that till tonight.